Okay, so our second speaker is Ben Wormleighton, lattice, and he's gonna from Washington University in St. Louis, and he's gonna tell us about lattice formulas for rational SFT capacities.
Hi, thanks for the opportunity to speak. It's good to be here. So I'm going to talk about new perspectives on newish capacities. This is all based on this paper that Julian Chaidez and I wrote and posted on the archive a few weeks ago. The lattice formulas is a reference to the kind of combinatorial flavor of this work. So the formulas that we're going to produce for these SFT capacities are combinatorial in nature, which is great because, as for kind of other similar combinatorial formulas for capacities in the toric case, that means computations become accessible. There's also going to be an algebro-geometric flavor to these formulas, and what that's going to do is it's going to mean we get embedding results for closed manifolds. Like algebraic surfaces, and stabilized embedding results for those two. Okay, so that's the general sort of picture we're working with. Let me do some setup. So we're interested in symplectic embeddings, that is smooth embeddings preserving the symplectic form. And in this talk, I've already said the word capacities, so I'm going to be focusing mostly on their obstructive aspects. So we're going to define and study invariants which obstruct embeddings. And the definition, which I'm sure much of the audience is familiar with, is a symplectic capacity is an assignment of some real number. I'll often use mathfrak letters in this talk to each symplectic manifold in some class, such that, well, they obstruct embeddings, such that if you have an embedding from x to x prime, and I'll use this curved arrow with an S on it to indicate the existence of a symplectic embedding. So if you have such an embedding from x to x prime, you're going to want your invariant to be increasing. And so if this inequality is violated, that means that no embedding can exist. So Carlos Siegel recently built a collection of capacities, these obstructions, using rational symplectic field theory. He was inspired by some ideas of Michael Hutchings. And these capacities I'll denote by R sub p of x omega. And this p, this index, is a tangency constraint for curves. So the sort of thing to have in mind is that p could be something like you have to meet a point p1 and also meet a second point p2 with multiplicity 3 relative to a local divisor. Sort of by a local divisor in this context, I mean a germ of a codimension 2 submanifold. Okay, so the P are kind of expressions of this form. I'm being very kind of informal here and continuing in being informal. Very roughly speaking, the way one should intuitively think about these capacities is that Rp is roughly the minimum over an appropriate set of rational curves of the area of this curve of curves satisfying this tangency constraint P. Okay, and so Carlos Siegel has some really nice work making this fully rigorous using the sort of L infinity formalism. But for now, I'm just going to leave the statement pretty informal like this. Okay, so the last bit of setup I need are the sorts of spaces that we'll think about, and I'll be focusing on toric domains. So let mu from Cn to Rn be just the normal moment map for the torus action on Cn. Then a toric domain, x omega, is given by some subset, maybe with some properties, I'll talk about that in a sec, inside Rn, inside the codomain of mu. And then x omega is simply the pre-image of this omega under the moment map. Okay, so these are really nice symplectic manifolds. Their capacities have been studied in various works. And I guess what we're doing is continuing that story for these SFT capacities. Okay, so the particular kind of toric domains we'll focus on are called strongly convex. So x omega is strongly convex if again, roughly, omega looks like the following. And the key thing about this picture is that the normals to the boundary of omega, or at least the boundary away from the axes, are all pointing in the positive orthant. They're all pointing in kind of the directions inside the positive orthant. You know, if we don't have any normals pointing outside, they're all pointing outwards in a positive direction. I'm not putting any constraints on the type of the boundary. I kind of tried to make it mixed in the sense that it's fine if the boundary is polytopic or piecewise linear. It's also fine if it's smooth or anything else. The only condition we care about is this normal condition. And so there are lots of spaces that fall into this category. Balls, ellipsoids, polydiscs, kind of wild things that you can draw just by drawing a curve with the appropriate normal condition. Okay, so like I said, for the ECH capacities, the Hutchings capacities, using S1 equivariant symplectic homology, there are great combinatorial formulas that have been found, that have been developed, and they in particular, among other things, make computations very accessible. It means that we have a kind of much better understanding of embeddings between such objects than other spaces. And kind of one of the places that my work and other work with Julian has come in is taking these combinatorial formulations, realizing them as things in toric algebraic geometry, and then using that to kind of leverage and get some applications to control embeddings into these like closed algebraic surfaces. So the main point of this talk is, or the main point of our paper, is that we analyze these RSFT capacities of Siegel for toric domains through this lens, in that we would love some combinatorial formulas so that we can do calculations, but we'd also love connections to algebraic geometry so that we can look at questions there. I've written with some differences, and the difference here, which I find really cool, is that the relationship between combinatorics and algebraic geometry is inverted. So for ECH, Hutchings, other capacities, the relationship to algebraic geometry came after the relationship to combinatorics. In this situation, to actually get a combinatorial formula, we had to pass through algebraic geometry. And so that's a nice feature. And it also means that some of these techniques can have some promise for situations outside of the toric case as well. Okay. So let me start telling you some of our main results. And throughout, we'll make this assumption that P is not just any old tendency constraint. We'll actually assume that it's a so-called lax tendency constraint. And that just means that the kind of incidence condition, the tendency conditions in P are applying to distinct points. So if we remember our friend from before, meet P1 and meet P2 with multiplicity 3 with respect to some local divisor. This is lax only if, well, if and only if these 2 points are different. So maybe just to draw you a picture, the 2 possibilities we could have if P1 and P2 were different, this tangent constraint looks something kind of like this. This is my little schematic of a point P1 and a point P2, and I've drawn a little local divisor nearby. This first constraint is asking me to pass through P1 and then pass through P2 with multiplicity 3. And this first picture I've drawn is lax because P1 and P2 are distinct. The second picture I'm going to draw, it's going to be a non-lax tendency constraint corresponding to P1 equals P2, where it asks not only do I pass through my point, but then I come back to it and meet it with high multiplicity. So this is the case that we'll be working with, and I'll make a comment later where this fits in. Okay. So sort of our first main theorem will also restrict to 4 dimensions. And again, I'll make some comments about where that comes in and where we can move past it. Suppose X omega is strongly convex for the toric domain. So coming from one of these omegas with this normal condition. Then there exist combinatorial quantities LK and UK, and I'm denoting them like as just with a single argument omega to make it clear that they're really combinatorial just depending on omega, such that LK lower bounds RP, and RP is upper bounded by UK. So we've sandwiched RP between 2 combinatorial quantities. And how does K come into the picture? Where the codimension of P is 2K. And by the codimension, we mean the amount that imposing P cuts down the dimension of an appropriate moduli space. So in essence, this is sort of the dimension or expected dimension of the space of curves satisfying this constraint P. Okay. Let me just pause here for a second, actually. Are there any questions on this statement? I'm going to present some variations on it. And so I just want to make sure that this statement is clear. Great. Okay, so for our second result, so we only had a sandwiching in general. If, in fact, our domain is kind of special, and if it is as long as it is wide, so we define these quantities A and B, which are basically the lengths of the bits of omega living on the X and Y axes respectively. If A equals B, so like I said, as long as it is wide, in that case, then actually the RPs only depend on their codimension and agree with the upper and lower bounds. Okay, so the way we prove this, as you might expect, is we show that in the case where A equals B, we have LK and UK agree. So in this case, we get exact formulas. And so this, this covers lots of situations like cubes or many other domains that you can design with this property. Okay. And I haven't told you what LK and UK are yet. I'll do that in a few slides. So like I said, one of the advantages of having algebro-geometric formulations of capacities is that you can often extend those embedding obstructions to also cover embeddings into algebraic surfaces or algebraic varieties in general. In the case where omega is a rational slope polytope, so that means it's a polytope and it's the normal vectors to each facet or each edge of its polygon are rational. It's just a technical condition, it doesn't matter that much. To such a polytope omega, we can associate an algebraic toric surface called y omega with an ample divisor a omega. And so I can use a omega to think of y omega as a symplectic manifold. And then what we find is that our UKs actually obstruct embeddings into y omega as well. So suppose omega is a strongly convex rational slope polygon. So if you like, it's in the intersection between domains that defined algebraic varieties and strongly convex domains. Then if X is any star-shaped domain symplectically embedding into the toric surface y omega, then the RP capacity is bounded above by UK of omega. And again, when the codimension works out. So we get embedding obstructions into algebraic surfaces. One of the advantages of Siegel's capacities is that they behave well with respect to stabilisation or taking products. So in the special case where we look at a tangent constraint just at a single point, to call it P of K, this is the constraint. You meet a point P, a single point P with multiplicity K plus 1. Again, as always, with respect to some local divisor. So this tangent constraint in particular behaves very well with respect to stabilization. And so we immediately get what is, to us at least, one of the first stabilized embedding results for closed manifolds or for algebraic surfaces. Let omega be rational sloped, strongly convex again. If X is star-shaped and embeds into the product y omega cross Z for some closed Z, then this capacity RPK of X is bounded above by UK plus 1 of omega. The discrepancy between K and K plus 1 is just an indexing thing. The point is, our UKs also provide obstructions to stabilize embeddings. I should say that these RPKs are also known as GK in some of Kyle's papers. Okay. Those are our main results. We can also use this, I'll maybe say a word about this at the end. We can also use these results to get information about the asymptotics of the RP as the codimension goes to infinity. And in particular, in this strongly convex toric case, we get an exact formula for what the limit should be. And RP grows linearly with the codimension.
So does that mean you have like a geometric understanding of this U and L stuff, or is it just some combinatorial magic that happens?
Yeah, so no, we have a good like geometric understanding of where the U's and L's come from. We don't actually have a good understanding of what the limit is geometrically. So we would love to better understand the limit. It's actually the last question. It's a question I have on my last slide is to do that. I'll show you the formula.
Thank you.
Cool. Yeah, so let me make some definitions and then show you kind of the big picture of how everything fits together. So for a convex set in Rn, we define the omega norm of a vector v in Rn, which is just the largest value you get by dotting things in omega with v. Then Lk is quite easy to write down. Lk of omega is the minimum over, maybe the best way of thinking about it is it's the minimum ranging over relations like this, where you have at least k plus 1 vectors of the sum of the omega areas of the vectors appearing. So you have some list of vectors, at least k plus 1 of them, they add up to 0, you take the sum of the omega areas of the vi, and you minimize that quantity, and that's Lk. Okay, so I'm not going to spend much time talking about Lk, I really want to get to the kind of intersection with algebraic geometry. Well, I will say this can be interpreted by our algebraic geometry, and I will hopefully make that comment in a little bit, but this comes from kind of direct calculations in SFT. And in fact, this is always just a lower bound for the RP in any dimension. You don't need dimension 4 for this. So UK, it's going to look a little bit weird, but I'm going to say where this weirdness comes from, and from an algebraic geometry point of view, it's actually very natural. Consider the following condition. I'll call it dagger. Suppose you have a sequence and it has at least 3 elements. If one of the vectors is equal to one of the basis vectors, E1 or E2, then dagger says there has to be a VQ which points in a different direction, which is not this EI you already had or negative EI. A better way of saying this maybe is we are excluding lists that look like this. So we're excluding lists that are just E1, negative E1, E1, negative E1, so on. If you have a list that looks like this, at some point I have to have some other vector v, which is neither E1 or negative E1. And then UK is simply the same minimum, the same optimization problem, except we range just over relations that satisfy this condition dagger. Like I said, this comes from algebraic geometry. So clearly UK is bigger than LK. I will say a little bit now about why RP should be sandwiched between them. Okay, so I only have a few minutes, so this is my kind of big picture schematic of how the ideas come together, and I'll try and make some comments that hopefully make sense. So our first piece is we look at curves in toric varieties. So old work of Badarev showed that curves in toric varieties can be realized, or classes of curves can be realized as relations between vectors. So for example, this is the fan for a Hertzsprung surface, for the second Hertzsprung surface. I've drawn numbers on the edges to indicate the relation. You take 1 times the primitive vector on this ray, plus 2 times the primitive vector on this ray, plus 1 times the primitive vector on this ray, plus 4 times the primitive vector on this ray, and you get 0. This is depicting a curve class inside the Hertzsprung surface. Okay, so all those times before where I wrote down, we're going to optimize over relations between vectors. Really what I was saying was we're going to optimize over curves and toric varieties. These curves, you can think of these positive numbers as saying, well, I'm going to take 2 times that vector, like 2 copies of that vector, or 4 copies of this vector. When these numbers are positive, that makes sense. These numbers are capturing some intersection multiplicity. And so having positive numbers, in other words, being able to think of that relation as a list of vectors, is equivalent to saying that you live in the dual of the effective cone, which in algebraic geometry is called the movable cone. In the case that omega is strongly convex, we get a really nice set of generators for the movable cone. So a really nice set of generators for relations of this type. They're obtained as the closures of certain 1-parameter subgroups. And we show that when we have dagger, we're able to represent every class, every one of these relations satisfying dagger, we're able to represent that in a nice way. And the thing that's motivating what nice means is that there's a Gromov-Witten invariant defined by McDuff and Siegel that basically gives you upper bounds on RP. So there's a Gromov-Witten invariant, GWYP, that when it's positive, get the area of that curve upper bounds the RP capacity of anything embedding into your Y. So the situation we look at is X omega, which essentially embeds into Y omega, and hence curves with non-zero Gromov-Witten invariant bound above the RPs of X omega. There's a really nice result, McDuff-Siegel, and this is where dimension 4 kicks in, that when you can represent your class with an immersed, positively self-intersecting sphere with big enough moduli, you get non-zero Gromov-Witten invariant. What we're able to show using our nice generators for this cone is that we can manufacture such a representative of our classes in our toric surface Y omega, and hence we pick up exactly the upper bound that we desired. Okay. So that was just a very loose sketch. I'm very happy to talk more about any of those steps. Questions, let me just leave you in response to Sarah's question. That the asymptotics we're able to produce come from the fact that LK and UK just have the same asymptotics. They're not that different. And so the formula we pick up is that the limit as codimension goes to infinity of RP over the codimension is this fun formula, which is some lattice formula. Again, it's kind of, you can formulate it purely algebro-geometrically, but we don't know what this limit capacity is. We don't have a good interpretation of it. So, yep, thanks for your attention. Very happy to answer questions. Thanks.
Thanks for the talk. Any questions?
How strong is the convexity requirement? Like how flexible can you be around this?
Yeah. So the LK, the lower bound doesn't need it at all. The one place right here is when we needed it, where basically these generators, these curves, you can still find them when omega is like not strongly convex. The problem is that you can't show that they generate the movable cone. You can't show that they generate all these relations. I don't think. Yeah, from the algebraic argument, I don't think there's anything particularly special about strongly convex. I think it's more just the case that, I mean, it may even be the case that optimizers, like relations that actually reach this optimization, you can always write in this form anyway. And that's what we found in examples. So I think the strongly convex assumption is not particularly integral to the UK upper bound.
Okay, thank you.
Do these capacities yield new results about embeddings, or something which you could not prove with old tools?
Yeah, I think so. So the kind of primary newest thing was that stabilized embedding result. This one, like I at least, maybe there were some in the literature, but I didn't know any kind of embedding obstructions for stabilized embeddings into like toric surfaces. So in particular, we can say some stuff about the Gromov width of y omega cross Cn or y omega cross other z with big Gromov width. Those are the main applications. In terms of their strength, the calculations we ran show at least for those kind of like fairly simple polytopes that we looked at, they were about the same as the ECH capacities for small codimension. Of course, the ECH has different asymptotics, so they're going to be much lower once codimension gets very big. But yeah, I think in our paper we had a few applications. A kind of Gromov width calculation for this was probably the main one we had.
Thank you.
Any other questions? Okay, if not, let's thank the speaker again.